I welcome you to this lecture of microscale transport process. What I wanted to talk about today is microstructured reactor. So far we have covered several aspects of microscale transport process, particularly these electrokinetic phenomena like electroosmosis, dielectrophoresis and topics like that. Also I talked about this slip flow, which is more important for flow of a gas, and how this first order slip boundary condition can be handled in a microquet or microporous flow that I discussed in the last class. In this class I briefly will touch upon certain issues of modeling a microstructured reactor. There are certain aspects of microstructured reactor. There are certain assumptions that can be made for a microstructured reactor. These assumptions would help simplifying the problem. Otherwise, you can always solve a problem from first principle and write a very detailed CFD model. However, when it comes to solving it quickly, when it comes to have a simplified model, I would like to talk about those assumptions that can be made for a microstructured reactor. I hope I will be able to finish this topic today, and from next class I will be discussing about transport of or flow of immiscible phases. That means two phases simultaneously flowing through a microchannel. So, this class I will be talking about some aspects how we can simplify the design of or the modeling of a microstructured reactor. Now, let me point out that this microstructured reactor, the reason why we have gotten into this microstructured reactor is that the reason we have gotten into this microstructured reactor is that you have certain advantages. The advantages are number one, a high heat and mass transfer coefficient due to short diffusion path. Number two is well defined flow pattern. Why I mention this well defined flow pattern is that the other candidate that could be, I mean, if you look at other modes of in other modes by which these reactors operate on an industrial scale, is basically packed bed type reactor, but inside a packed bed the channels are pretty random. That means, in some places channels are wider and in some places channels are too constricted. So, the flow pattern is not well defined, and if the flow pattern is not well defined, you do not know what type of heat transfer mode or mass transfer mode would be working there, and more importantly, it could be that some places inside this packed bed, in some places the weight of or the amount of catalyst that is available per volume of influent is much higher, and in some places it is much lower. So, having a control over the conversion, having a control over the side reactions, or having a control over the heat of reaction that is generated or heat of reaction that is absorbed. So, that control becomes difficult if you have that random pathways. So, here in this case you have well defined flow pattern. That means, what I mean, you remember how we described this microchannel reactor. These are basically a very structured honeycomb type structure. So, you have a monolith. That means, have you seen a honeycomb? You have a monolith, and in that you have channels engraved. So, these channels are running parallelly, but these channels are very well defined. That means, the aperture here or the cross section here and the cross section here and the cross section here, they are same. So, you have a monolith and you have these channels running. So, so basically you first I mean if you ask me how do you generate this, basically you have a monolith first and then you wash coat it. That means you apply a coating of catalyst on the wall of these channels. So, that is how you generate these catalyst monolith, and now you have flow going through these channels. Okay. In case of a porous in case of a packed bed, what you have is you have the same packed bed, only thing is you have those catalyst pellets here, and the flow was flow was forced through these constrictions. So, in some places channels are wider, some places channels are not. So, amount that is what I said. First of all, the flow pattern is not well defined. So, you do not know in which regime you are working, and also you do not know what would be the catalyst that this flow encounters per unit volume, and that probably defines how much how fast the reaction would be, or whether there should be any side reaction or not. And if there is too much of a reaction than what you want, there could be a possibility of thermal runaway. That means, there would be if it is exothermic reaction and too much of heat gets generated, that you do not have any procedure to control, then the catalyst would be spoiled by that heat. So, these problems are there. So, in case of microstructured reactor, you can get rid of these. Anyway, these are some of the issues that we already know probably. Number 3 is that surface to volume ratio is high. So, what this implies is surface effects dominate over volumetric effect. So, because of these advantages, you have these basically these microstructured reactor, these are good candidate for heat and mass transfer limitation. Think of a reaction which is highly exothermic or highly endothermic, and you need to if you need to run that reaction at a precise temperature. So, in that case, having that control in a packed bed is not easy. However, this microstructured reactor that promises that it can be done in a better way. Now, what we must say here is that this, when it comes to modeling these, I mean, of course, you can say that we can do it in a using the standard the theories that are available for CFD. That is in fact the right way of doing it, the rigorous way of doing it. However, we are looking for some assumptions that can be made such that some simplified approach can be developed. Now, when it comes to developing a simplified approach, I see there are basically 3 approaches possible. One is treat this microstructured reactor as a porous medium. Second is use something called a mean field model based on volume averaging, and the third is the rigorous approach. Third is the rigorous approach. So, this is actually this is going to be the simplest one, the porous medium based model. This is somewhat complicated, but it does not take care of all the I mean it still makes some assumptions, and the third one is the rigorous approach, which you should be doing, treating the 2 fluids and solving Navier-Stokes and heat balance and mass balance equation over a differential element, the way we do it for a standard standard flow reactive flow problem. Now, what is this porous medium model? porous medium. So, these channels, I said that it is like a honeycomb, right? It is like a honeycomb. So, you have these channels which are running along the length of the reactor. Rest of the matrix is what? Solid, right? These are solid material, and in that you have channels running. Now, if you want to treat this as a porous medium, then what you would be doing is, let me draw this how it will appear. This is the solid part, this is the open part through which the flow can pass. Again this is the solid part, again some open portion, then again there is a solid part and this open portion. Suppose this direction is x, this direction is y, and this distance is w, whereas this distance is w c. One is the channel and the other is channel plus the solid part. All right. So, you have a series of this, not just 3, thousands of them. Now, what we must say here is that the incoming flow is distributed over large number of channels of width W c separated by walls with a width of W minus W c. So, there are walls, the width of the wall is W minus W c and the width of the channel is W c. This I think this should be, this is understandable. Now, I think you are familiar with a theory called Darcy's law. If we apply that, it would appear like this: d d y of P f plus epsa mu divided by k u f, that is equal to 0, where epsa is equal to so called porosity, which is W c by W. Basically, you have another dimension added to it. Basically, porosity is considered volume by volume, volume of void divided by the total volume, right. So, here you have only one dimension you are considering. So, other two dimensions needs to be multiplied to this. Okay. So, you are considering that these two dimensions would be multiplied in the numerator and denominator, they just cancelled out. And k, typically this is for a, this is considered permeability for a porous flow through porous medium. Now, this has been shown that when you have a channel and if you want to find a permeability for a flow through a channel, there is an expression available. When you have two flow between two parallel plates, okay, two parallel walls, and that the flow through that channel which is made by two parallel walls, you can come up with an expression for k, and that expression is given by epsa W c square divided by 12. That is how it is given. Or what you can do is, I mean, if you well, this is the expression. This expression has been obtained by one researcher in some time back. This is later on one researcher from University of California, Berkeley, he first in his PhD thesis he proposed this expression. I mean, that's what I hope I am right. I mean, I remember, that's what I remember, and later on this was referred as cubic law. So, this is how this permeability can be defined for a flow through a channel. So, now you can let me point out a couple of things here before I go further. P here is pressure, U here is velocity, and this quantity, something in this kind of bracket with F written as a subscript, these represents average over fluid phase, average over fluid phase. All right. So, this is how this pressure and velocity they can be related if you consider this to be a porous medium. Now, let me write the full form in what all we are doing here. The other issue here is the heat transfer, which is written as 1 minus epsa Cs rho s del T plus C g rho g u bar del T del x, that is equal to lambda del square T del x square plus heat of reaction minus losses if any. This I am saying this is how it is considered, the heat transfer, the heat balance equation. What are you doing here? I mean, can somebody guess what are we up to? Why, I mean, what is prompting us to write it this way? We are talking about only one temperature. Have you noticed that? Whose temperature is this then? I am talking about a monolith, I am talking about some portions are solid material, then I have a coating of catalyst on the wall which is helping me achieving the whatever conversion that I want to achieve, and I have a flow going on through these channels. Whose temperature is this now, and how are we writing this? So, that could be a, I mean that is well lies the assumption. You are treating these to be as if it is a single medium and it has temperature. I mean, I have temperature as a function of time, temperature as a function of x I can see, okay, or should it be should it be y lambda, this should be del y we have considered this direction. So, flow is going on in this direction. So, actually we are looking at del t del y here. So, in that case this should be y not x. So, we are considering this temperature as a function of time and position, that much is understood. However, you are considering only one temperature. So, at least I mean what you how you are treating this medium is as if this medium is just a homogeneous bed, and in that temperature is just at one point the temperature, there is only one temperature. That means, whether it is a fluid temperature or solid temperature, you are assuming that they have equilibrated. These two, say a fluid at this point and the solid nearby, they are all equilibrated. There is not any difference in the temperature of fluid and solid. Say we are talking about a point here a point here, the solid temperature and fluid temperature, you are not differentiating it, you are treating it, I mean you are giving the temperature a function in position, temperature as a function of time, but solid and gas you are not separating, you are considering only one temperature. You are considering that the solid and gas, they are in equilibrium inside the medium. So, that means fluid is flowing, say as this travels from the bottom to top, fluid is flowing. So, at any point the fluid and the solid temperature there, they are considered same. That is how this equation is to be solved. This is possible when the channel dimension is really small. This type of assumption is considered in porous medium. When the channel dimension is small and the gas is flowing through that channel, so in a macroscopic sense you can consider that the gas and the solid at that point, these two temperatures are same, they are equilibrated. Okay. This is of course not a rigorous approach, that is what I said, this is an assumption. So, what you write here, I mean I should be writing here in this case is that above equation assumes thermal equilibrium between the fluid and solid phase single temperature filled. You remember velocity filled, velocity depends on position and time. So, single temperature filled is used for fluid and solid phase, fluid and solid phase. This assumption is this is told that this assumption breaks down at high Peclet number, at large Peclet number. This assumption breaks down. All right. Now, so you understood what how we have approached this porous medium problem. I mean, let me recapitulate once again. Let me repeat. We have come up, we said that it is the way we have defined WC and W is obvious, and if we add another dimension to it, a porosity can be defined by WC by W. Basically, other two dimensions need to be multiplied to the numerator and denominator, they have cancelled out. This basically porosity is defined as the volume of void divided by the total volume. There is an expression for permeability which you can this you can check in the Darcy's law, which has been there for quite some time. This Darcy's law, it basically that this will come directly from there. And this permeability term, which is this Darcy's law, is typically used for porous medium. However, that same equation can be applied for a flow through a channel where permeability can be given as this quantity, aperture of the channel to the power square divided by 12. Okay, so that is how you define, and this is referred as cubic law. And here in this expression I have mentioned P as pressure and U as velocity, and this quantity within bracket with a subscript F, this represents average over fluid phase. That means we are talking about UF. This is averaged over the fluid phase. We are not within a fluid phase, we are not differentiating layer by layer or any profile, we are not adding here velocity profile or anything. Now, you come up with the temperature the heat balance equation. Ideally, you should have two temperatures, one for the fluid, another for the solid, and the fluid temperature should have a profile within the channel. So, their temperature would be maximum or depends on whether it is exothermic or endothermic reaction. If it is exothermic, probably the temperature would be maximum at the center of the channel, and then at the wall it would be, or as you proceed towards the wall, the temperature should be less, and then there should be a continuity of flux at the interface between solid and fluid. I mean, there are all kinds of things which needs to be considered if you are really looking for a rigorous CFD model. However, we are looking for assumptions, because what you may be asked to do is to take up various dimensions of this microstructured reactor. If we change, if we take W as this, WC as this, and this material with property CS is this, rho S is this, and things like that. So, if you have to play with this and come up with the best design for your microstructured reactor, probably this kind of simplified model would be useful, at least to screen the I would say you have a large bound to play with. Now, if you want to come up with an optimum design, you need a simplified model first to focus on which dimensions or which materials or what you need to look for, and then probably you can get to the detailed rigorous CFD model to fine tune the results. So, that is what we are talking about. So, this simplified model is meant for a particular purpose, and by now you must have understood the purpose. Now, what we have here is the next topic is this. So, this is porous medium. This is the most simple model that I have that I had to talk about. The second model is mean field model based on volume averaging. Mean field model based on volume averaging. Okay, what you do here is if you have this distance is WF and this distance is WS. Similarly, this distance is considered HF and this distance is considered HS. Okay. And you are considering x in this direction, y in this direction, and z in direction perpendicular to the paper. So, flow is taking place perpendicular to the paper through these channels. All right. Now, if you need to find out what is the phase volume fraction, that means what is the fluid volume fraction in this reactor. So, if I call this phase volume fraction, or let us call this fluid volume fraction, and there are two volume fractions, one is fluid, another is solid. So, fluid volume fraction, that is equal to WF HF divided by WF plus WS into HF plus HS. All right. This is how you define the fluid volume fraction, and this we call is equal to phi f. Okay. And then the solid volume fraction, that is phi s, which is equal to 1 minus phi f. Okay. Now, if we try to write the heat balance equation, this will take the shape. I mean here what we will be doing is we will be treating the temperature of fluid and solid separately, but it will not be a full rigorous model. So, the heat balance equation would be rho f C f del del T plus U I del del X I of T f, that is equal to minus alpha A V T f minus T s plus S C. S C is a generation term, generation from reaction term. For the solid, you have del del T of T s, no convection possible within the solid, and that is given by some conductivity tensor, thermal tensor, and that is del del x I del del x j of T s minus alpha A v T s minus T f. All right. This is how you want to write this expression. Now, let me clarify the meaning of various terms. I will use another page and I will come back to these expressions after I define all these terms. Okay. Here alpha is equal to heat transfer coefficient from channel wall to fluid, and A v is equal to specific surface area, that is equal to wall surface area divided by reactor volume. U I is equal to velocity of fluid averaged over the channel cross section. Here rho f is equal to phi f into rho f 0. Rho f 0 is basically this subscript 0 refers to material densities. Material density, because we are talking about a rho f. So this rho f, as far as this bed is concerned, this has to be multiplied by the void volume fraction or the phase fraction of the fluid, then you get the actual rho f, which should be applicable for this equation. Here we are working on a mixed mode. I mean, it is not very straightforward. You need to look into it very critically. We have this as rho s 0. This 0 refers to material density. So rho s is equal to, so think of it. We have a rho f here, we have a rho s here, but these rho f and rho s, they are not the density of the solid and density of the fluid, rather they are pure component density of the solid multiplied by the corresponding void fraction, how much solid, what fraction the solid is occupying within the bed. So then only we can make this, we can do this treatment. Okay. SC represents thermal energy from a chemical reaction. And this model describes, of course, we have to define this CF and CS. CF and CS, they are fluid and solid, specific heats. Okay. So, the model describes average temperatures of fluid and solid without incorporating local fluctuations due to temperature gradients within single channel or channel wall. Then now the question would be how you handle this Kij, this term. How will you get Kij? So, this is not neither a property of the neither the thermal conductivity of the solid material, it cannot be treated that way. So, what researchers have done is they have come up with they have used something called a theory of network of thermal resistors. It is a network of thermal resistors, and what they have done is they have obtained Kxx as Wf plus Ws into Hf plus Hs divided by Hs into Wf plus Ws inverse into Ks Kyy, this is equal to Hf plus Hs into Wf plus Ws divided by Ws into Hf plus Hs and Kzz phi s into Ks. This follows from theory of network of thermal resistors. So, if you here you have thermal resistors, but how is it aligned? I mean, think in that line. How is it aligned? You have one channel, then you have another. I mean, think of it. There is one channel. Then this is connected to another channel in this direction. This is connected to another channel in this direction. This is connected to another channel, and then you have these porous the voids through which the gas is flowing. So, you have these theory these network of thermal resistors. There are certain theories, and people have already researchers have already utilized those theories to come up with these expressions for Kxx, Kyy and Kzz, and what all other components of thermal conductivity tensor vanish, because what was the equation here? This was the equation, right? This was the equation originally for mean field model based on volume averaging. We have for the fluid phase rho f Cf. Now, we have already said that there is a correction for rho f. So, rho f Cf del del T plus. So, you are operating this entire you are putting this operator on the Tf, that is equal to minus alpha Av, and this is the heat exchange term between fluid and solid, and plus some generation term. Similarly, for the solid you do not have a convective term. So, it is only the transient, and then you have the thermal conductivity. So, this is how you write, and then what you how did we treat otherwise? It would have been lambda del square T del z square, or that way we or del square T del x square, or you write it as lambda x del square T del x square plus lambda y del square T del y square lambda z del square T del z square, things like that. But ideally you should be writing it. This is the most generalized way of writing it. Now, this is the thermal conductivity tensor. What we are with these assumptions of mean field model and network, rather more importantly the network of thermal resistors, what they have come up with is that these Kxx, Kyy and Kzz, they are existing, and this is the value, and we have related WF, WS, HF, HS, all these things. We have come up with a very neat functional form here. Of course, I have not the equal to sign, but approximately equal to sign, okay. And then multiplied by Ks. Ks is the actual thermal conductivity. It is a bulk property. It is a pure component property of the solid. So, this is the pure component property of the solid. If there would not have been a channel, there would not have been a fluid passing through this solid, then we would have considered simply Ks. Okay, but now since we have these channels and we have, so we have now a thermal conductivity tensor, but what we are, with some simplification, what you came up with is that Kxx, Kyy and Kzz, these are the values you have, and all other components, the cross terms, all other components thermal conductivity tensor vanish. So, now you should be, now it is much simpler to handle. Okay. You must appreciate at this point what is the difference between a porous medium model and mean field model. Porous medium, there you did not have, you just have a single temperature. Porous medium model, you have just one temperature, you did not differentiate between the solid and the fluid. There was just single temperature and you said they are all equilibrated. Okay. Here you are having two temperatures, Tf and Ts. You are working with two temperatures. However, you are treating that this you are assuming that these average temperatures of fluid and solid without incorporating local fluctuations. So, you are not considering any temperature gradient within a channel. I mean, within a channel where the gas is flowing or the feed that is going through, or next to that the solid material, there also you will have a temperature gradient, but you are just putting a Tf and Ts. You do not differentiate between Tf at the center of the channel and Tf at near the wall of the channel. So, you do not differentiate them. So, you make certain assumptions here. You do not have since you do not have this, you are not considering any proper boundary condition at the wall of the channel, that the fluid, okay, this is the fluid temperature, you have this as the you have the solid temperature, you have the continuity of flux, etc., that you are not considering. Rather, you are clubbing everything together and you are using this alpha Av Tf minus Ts, this term, for the crosstalk between the fluid and the solid. So, this is, I mean, you can see this is a very mixed approach. I mean, you have made certain assumptions, again you are retaining Tf and Ts. So, one thing you must appreciate, that this mean field model based on volume averaging, this gives you a somewhat, it should give somewhat better, somewhat more accurate result than porous medium, but this is not 100% rigorous. And why volume averaging? Look at it, how you have considered rho f. For example, the rho f that you used here is phi f into rho f 0, rho s is equal to phi s into rho s 0, and that is what you have used in this equation. You think about this equation, I mean, it is not absolutely straightforward. However, this can be very useful if you want to get some quick result in a sense that you are given 10 choices. Okay, you can have Ws as this, Wf as this, Hf as this, Hs as this, and you have the properties Cf, Cs, etc. are given. And now you tell me what should be the best design of the reactor. Okay, what should be the best material for the solid part. Okay, if you have to scan through it and come up with a between these bounds, what would be the best result you have. So, if you want to do such quick calculations, then probably if you start from scratch and do it a detailed CFD model, that that may require time, and it can save some time and give you some quick idea as to where you should focus on, which part you need to play with, so that you can get a better, more optimum, more efficient reactor. So, this is what we have. Now, let me see what we have one component left, because we started with, you remember, porous medium, mean field model based on volume averaging, and a rigorous approach. So, these are there. Now, you need to understand that And one thing I must point out here, that in this mean field model, when you work with this kxx, kyy and kzz, you have definitely made note that in the xy plane, what is the xy plane? Whatever is the xy plane, I remember the way we define mean field model is z is perpendicular to the paper and the flow is happening perpendicular to the paper. So, the other plane, the cross section is xy plane. No conduction within the fluid without intermediate heat transfer to the solid walls. So, this is something which you are basically considering you very tacitly, that you have two channels side by side and in between you have a solid, right. You have two channels going side by side and you have in between flow is happening perpendicular to the paper, and this is what you have. This is the block through which the flow is taking place, right. So, conduction, the heat transfer between this and this is not permitted without going through this solid part. That part you have assumed here. So, that needs to be understood. Another thing is this heat conduction in z direction is typically negligible compared to convective transport, negligible compared to convective transport. This is heat conduction in z direction. Z direction is in the direction of the flow. Typically, the heat conduction in z direction. I mean, I have a kzz term, and this kzz term is very much there. Kzz term is very much there. So, heat conduction is possible. However, the temperature gradient in z direction, that is something which is probably causing you this heat conduction in z direction is not very significant. I mean, if you look at this honeycomb, I mean the way these honeycomb reactor they operate is that you have, suppose you have a block of this structure, and you have several such channels running parallelly, very well defined channels. You know exactly the dimensions, and inner wall of these channels are coated with catalyst material. Okay, you have dipped this whole structure into the catalyst material, and you have a coating of that catalyst, and that is acting as a catalyst when the flow is taking place through these channels. Now, there will be a heat of reaction, maybe it could be exothermic or endothermic. So, it could be either heat would be generated or heat would be taken by the reactants. So, either you have to take out the heat, I mean unless this heat of reaction is small, either you have to take out the heat from here or you have to give the heat. So, if you have one such block and then you have another block, you have one such block and then you have another block here, in between you have one layer where through which you pass the either the heating or the cooling fluid, and then you have another block on top of this, and in between you pass the heating or the cooling fluid. So, what is happening here? You are having a flow here, this is your z direction, right. Now, you have difficulty, I mean see, so where would be if in this direction, maybe x or y, I mean the transverse direction, z is in the direction of the flow. So, perpendicular to this in the transverse direction, you have, I mean what do you expect? Suppose here there is another heating layer. Suppose you are talking about the endothermic reaction, that means the feed is taking the heat, so you are heating, you have a heating layer. So, you are having a hot fluid flowing through this, or by some other means you are heating this layer, all right. So, you have this heating layer here, this heating layer here, then which place would be the coldest within this block? It should be the center, right, by symmetry. So, this area would be the coldest, and here it would be the most heated, here it would be the most heated. So, you can expect within this block there is a temperature profile. Okay. Now, this block has thousands or millions of channels, I mean that is other issue, and the feed is flowing through this channel and they are taking the heat. When the gas is flowing through this channel, it is absorbing the heat, right. So, these we are talking about the temperature profile in z direction, and what I mentioned here is heat conduction in z direction is negligible. What I mean is, what is important to you at this point is that you should have proper heat conduction between this layer to here and this layer to here, so that there isn't a substantial temperature drop. Okay. Suppose you are doing why are you getting into microstructured reactor? Because you want to precisely control the temperature at which the reaction takes place, because you want to avoid the side reactions. Okay. Now, these, if it would have been a packed bed, you can have a similar arrangement in place. You can have a packing and then you have a heating layer around, but since it is a packed bed, since the flow this flow pattern is not well defined, what you end up with is a temperature gradient within the solid. So, you would be ending up with, suppose you are supposed to maintain it at say 1000 degrees centigrade, and you have a gradient of say 40 degrees centigrade. So, 960 degrees centigrade is the temperature at which the center or the core of this is operating. So, you have a gap. So, you are supposed to maintain it at say 1000, you are maintaining the wall at 1000, maybe it is the reaction should be occurring at say 980 degrees centigrade. Now, you have that window you are creating, and so you are producing side reactions, you are getting into other things. Now, the reason this you are choosing a microstructured reactor is that this temperature, that delta T, you can minimize. When we are talking about 1000, we are talking about 1000, 995 to 1005. Okay, that window is going to be smaller in these in microstructured reactor, and that what we are more concerned is how this heat conduction is taking place, because these solid material that you have should be a good conducting material, so that you can have the flow of heat in transverse direction. Now, whether what heat conduction you have in z direction or I mean that is immaterial, because anyway the main method by which the heat is transferring in z direction is by convective flow. The fluid is flowing in z direction. So, that is probably what I mentioned here is, as heat conduction in z direction can be negligible. I mean I know some students who worked here where they have considered this z direction heat conduction as well and compared and showed to what extent it can be negligible, but this is one fact which I think you understand what I want to mean by this statement. Now, we have I would like to make a quick comparison here, is that if you now plot temperature versus z, temperature versus z, z is perpendicular to the paper, that means z is in the direction of flow. So, in the direction of flow, if you now plot, you will find that you will have one is meant for the solid and other is meant for the fluid. And in case of a porous medium type model, you have assumed that this fluid and solid, they are of same temperature. So, you had single line for porous medium model, you had single line, at least you have two different lines from this mean field approach, and these are temp T at where, I mean T is probably at center line of the reactor, these as a function of this. So, in case of porous media model, you will have a single line porous media model, you have a single line for solid and fluid. For mean field model, you have two separate lines However, the issue is that an approximate value of thermal conductivity was used. So, you have computational time here is saved, however, the accuracy is sacrificed. If you I mean, I am not going to discuss this rigorous model, but you know what this by rigorous model what we expect, that inside the channel you have within the channel, within the fluid phase itself, in a single channel there would be a temperature gradient, there would be a velocity gradient, and there would be continuity in heat flux at the wall between the fluid and solid. So, if you consider those, your computational time would be higher. In mean field model, the computational time is saved, however, the accuracy is sacrificed, and this I mean the empirical the experience says that this accuracy is of the order of 2 to 3 Kelvin for total temperature range of 35 Kelvin. That is some people have found, in some researchers have found showed that if you do this, you sacrifice the accuracy, but this sacrifice of the accuracy is also can be quantified, and this is not a very large quantity. I mean, at least you can do the screening of the material, screening of various geometries using this method, and finally get the final result using a detailed CFD model. And these so you can compare the thermal performance using this mean field and the porous media model. You can compare the thermal performance of different reactors, and because to compare the performance you need to run it several times, and probably that would be the computational time would be a concern if you use a rigorous model. So, I think you understood what I mean the how some approximations can be done, where you and still you can get some result, some approximate result for these microstructured reactor. In the next class, we will be discussing about the as I said, immiscible flow through microchannels. We will start with first the definition of Laplace pressure, and then we go from there. That is all I have for today's class. Thank you very much.